Today we're talking about vectors, and we're going to talk about the geometric side of vectors. Before we start going through the geometric vectors notes that you guys have, we are going to go through just sort of some background on vectors, and we're going to talk about something called a directed line segment, just briefly. This information will be helpful when we get to vectors, so please make sure you're paying attention and writing down this information in the formulas that you see. So a directed line segment, a vector is a directed line segment. It is a line segment that has an initial point, so that's a starting point, a terminal point, which is your ending point, and then magnitude, and magnitude is your distance, or your length. Now, what I have is a picture of a directed line segment, P to Q. P is our initial point, or starting point. Q is our terminal point, or our ending point. And the magnitude of PQ, the distance between P and Q, or the length of segment PQ, is written with those double bars on either side. And it is a formula that you should recognize because it is the distance formula. Now, the magnitude is your terminal point, so your terminal x value, your ending x value, minus your initial x value, squared, plus your terminal y value, your ending y value, minus your initial or starting y value, squared. And then you take the square root of those things. And again, this is the distance formula. We've been using this since before geometry to find the distance between 2 points. And that's all you're doing is you're finding the length of segment PQ using the distance formula. Now, we can take a directed line segment and we can write it in component form, which is the form we'll be using to talk about our vectors. And what component form is it tells you from the starting point to the ending point, from the initial point to the terminal point. It gives you the distance traveled in x and the distance traveled in y with direction. So this is our x sub q minus x sub p is our x distance, and the y sub q and y sub p is our y distance. And so that gives us the distance between the initial point and the ending point for both our x's and our y's. And those are two different distances because there's a change in x and a change in y. Please note that this formula, the distance formula, and your component form of a vector, that those two things look the same. And that's going to be really useful to us because we don't necessarily have to do these calculations under a square root sign if we just write a vector in component form first. So we are going to be using component forms when we're talking about vectors. And that means that calculating the magnitude or length of a vector is easier if we just write the vector in component form first. We take that initial point and terminal point and put it in component form. All right, so let's look at an example of how we do this. So this is an example of confirming equivalent directed line segments or vectors. And in order for two vectors or line segments to be equivalent, they have to have the same magnitude and the same component form. And so what we're going to do here is we're going to get to practice twice putting a vector in component form and also calculating its magnitude. So that's step one for both of these. Let's go ahead and for vector A, which we write with an A and a little like half arrow on top of it, that tells us it's a line segment with direction. So it's a vector is a line segment with direction. To write vector A in component form, we use those little arrowheads and we say, all right, I'm going to take my terminal point and I'm going to take the x value from that, so that's 2, and then I'm going to subtract the x value from my initial point. So that's 1. And then comma, I'm going to take the y value from my terminal point, which is 3, and subtract the y value from my initial point, which is 0. And then I close my little arrowed point there. So this is 1, 3. And so what that tells us is from its starting point, this vector moves right 1 and up 3. That's what that tells us. So from its initial point to its terminal point, this vector moves to the right 1 and up 3. And you can see that in our picture. From the initial point, we go right 1 and up 3. So that is component form of vector A. Now, if I want to calculate the magnitude of A would be written with our double bar. And what you do is, I'm going to go back a slide just so you can see, magnitude is this distance formula right here. But remember that in finding component form of our vector, we already did those subtractions. And so instead of having to put 4 numbers under a square root sign, we just take the pieces of our component form and put them under the square root sign. So the distance between these points, the magnitude of A, is equal to the square root of the change in x, and that for us was 1, right? Our from initial to terminal, our vector moved to the right 1, squared, plus the change in y, and for us that was 3, because from initial point to terminal point we went up 3, squared. And so that is the square root of 1 plus 9, which is the square root of 10. And leave that. We're just going to compare. So we don't need to simplify the square root. Just leave it the way it is. So now I know for vector A, I know my component form, which is 1, 3, and I know my magnitude, which is the square root of 10. In order for me to confirm whether vectors A and B are equivalent, I also need component form for B and magnitude for B. And again, component form is just the way we write vectors. It's inside those little arrows, which we call chevrons. And magnitude is just the length of the vector. All right, so I'm going to calculate these things for B. So vector B, and again, we write vector B with a little arrow over the top of it, indicating that it's a line segment with direction, is equal to, in component form again, is I take my terminal point and subtract my initial point. So here my terminal point is the 1, 7. It's our ending point. And my initial point is the 0, 4. So I take my terminal x, which is 1, and I subtract my initial x, which is 0. And then my terminal y, which is 7, and I subtract my initial y, which is 4. And when I do that, I get 1, 3. And so again, component form of B is 1, 3 inside those chevrons. And then I also want to calculate the magnitude of B. And again, the way I do that is I take the distance between my x's, my change in x, square it and add it to the change in y, squared, and then I take the square root of all of it. All right, it's the distance formula. And so my magnitude for B is equal to, now we don't actually have to calculate that change in x because we did it when we found component form of the vector. When we wrote it in vector form, we already found those distances. So this is 1 squared plus 3 squared. And that is the square root of 1 plus 9, which is the square root of 10. And so now I have component form for B, which is that ordered pair in a chevron, in the chevrons, rather, in those little arrows. And I also have the magnitude, which is the square root of 10. So now we've calculated component form for vectors, right? We take the terminal x and subtract the initial x, comma, terminal y, subtract initial y. That's our component form. And we have also calculated magnitude, which is we take the x from our component form, which is our change in x, and square it, add it to the change in y from component form squared, and then take the square root of it. So we've done that. And now we can ask ourselves, are these two vectors equivalent? Is vector A equivalent to vector B? Are they equivalent? And the answer is yes. And the reason they're equivalent is because their components forms, oh my goodness, typos all over the place, guys. And magnitudes are equal. So these are equivalent vectors. Now, you are not just, for your assignment, not just comparing vectors, okay? We do need to be able to write vectors in component form, and then we also need to be able to find magnitudes separate of comparing two vectors to each other. Now what we're going to do is we're going to look at the geometric vectors notes, and we are going to go through adding vectors, subtracting vectors, and then multiplying vectors by numbers to see what happens when we do that. So, a vector is any quantity that has both magnitude and direction. It can be represented geometrically as a directed line segment, which is what we were talking about before. The norm of vector v, denoted by the double bars with v in the middle, is the magnitude. And remember that we know that magnitude is length. The magnitude of a vector can be determined by applying the Pythagorean theorem, which is what we were doing. Distance formula and Pythagorean theorem are the same thing. I described the calculation for magnitude as the distance formula. These two things are the same thing, but that's the formula that we used twice in the last example. I'm going to write distance formula here. All right, and so then for example 1, they said if vector v is -3, 5, find the norm, which is the magnitude. So we're finding the magnitude here. And remember that the magnitude is just that application of the distance formula, right? So this is the square root of my change in x, which in this case is -3. So -3 squared plus my change in y, which is 5 squared. And that's our distance formula, right? It's an x value minus an x value squared plus a y value minus a y value squared. Well, they already did that subtraction for us, so we just put those two numbers under our square root sign. So this is the square root of 9 plus 25. Remember that negative numbers squared are positive, which is the square root of 34. And so the magnitude of vector v is the square root of 34. Now we're going to talk about adding and subtracting vectors. When you add two vectors, so we've got three little subsections here. The first one deals with adding two vectors that share an initial point. But it really doesn't matter whether the vectors share an initial point or not. The process by which we add the vectors together is the same. And so when you add vectors, what you do is you take the first vector that is in your addition problem. So in this case, in this first little box here, we are adding vector v to vector u. And so vector v is my first vector. And so I leave vector v where it is. And what I do is I take my second vector and I redraw it with its initial point at the terminal point of v. So I connect the beginning of vector u to the end of vector v, the point of vector u to the arrow of vector v, and redraw u in the same direction it's going with the same length that it has. And so I'm going to do that here. Again, v is my first vector, so it's going to stay where it is, and I'm going to redraw u with the same length and the same direction. And so here is my redrawn u. And then to find vector v plus vector u, v plus u, I draw a vector that goes from the initial point of v to the terminal point of my redrawn u. So from the beginning of v to the end of the redrawn u. And in this case, for this example, the v plus u that they've given us is a little short. And so really, v plus u should look like this. Should look like that pink line. And so again, it's from our initial point of v to our terminal point of u. And it starts at the initial point of v and ends at the terminal point of u, so the arrowhead is on the point up by u. And so again, the way we do this is your first vector stays where it is. Your second vector in the addition problem, right, the first stated vector, in this case v, stayed where it was. The second vector u, we redraw it with its initial point at the end, at the arrow end of v. Redraw it. And then to find the sum of the two vectors, we draw a third vector going from the starting point on v to the ending point of the redrawn u, the starting point of the first vector to the ending point of the redrawn second vector. The same thing happens for this second example, this middle box, where it says add two vectors that do not share the same initial point. They say draw up representations of the two vectors such that the initial point of one coincides with the terminal point of the other. Well, in this case, they are adding u plus v. That's the way this problem is going. So u would stay where it was. We would not move u. And then we would redraw v so that its starting point is at the end of point u. So initial v is at the terminal side of u. So starting point of v is at the end of u. So there's v. And then again, what you're doing is your sum here, the addition of the two, would be from the starting point of your first vector, in this case u, starting point of your first vector would be the beginning of our sum, to the ending point of the second vector, and in this case it's up here. And that's vector v. And so that's our sum. The pink vector is our sum. Now, for subtracting vectors, we do an additional step. For subtracting vectors, we do an additional step. So if we have vector v minus u, that is really v plus, it's addition, negative of vector u. And so what we have to do first is we have to reflect vector u. So you see in our problem here, they gave us vector v, and then this is vector u. And then when we go to do the subtraction, what they've done is that they flipped the beginning and ending points on u. So u started at the bottom and ended at the top with an arrow. Now u starts at the top and ends at the bottom with an arrow. And so what they did is they flipped u, made it negative. And then they did the initial point of u at the terminal point of v, right? We put our starting point for u at the ending point of v, and then drew, again, your sum vector, right? This is v plus negative u from the starting point of v to the ending point of our redrawn u. And we're going to do a couple more examples of this, so if this is a little confusing, don't worry too much. All right, so we're given vectors v and u here, and so what we're going to do is we're going to draw the sum and difference of v and u. And so we're just going to do our best to estimate v and u when we redraw them. So for both of these problems, v is the first vector, so it's going to look pretty much exactly as it looks over here in our in our problem, our example, what they gave us. So for number 2, vector v looks kind of like that, and I'm going to redraw it as it appears there. And then if I want to add u, what I do is I put the initial point of u at the end of v. So I come up to the end of v, and that's my starting point for u, and then I draw, again, an approximation of u. It's shorter than v, and it's going off to the left. So that's my u. And then the sum of the two will be the vector from the initial point of v, the starting point of v, drawn to the ending point of our redrawn u. So this is v plus u, like that. And so they make a triangle, basically. The two vectors you're adding or subtracting, the sum or difference of those vectors makes the third leg of a triangle. They make a triangle. All right, so for v minus u, remember that I said that this is v plus negative u. And so what we're going to do for this problem is we're going to flip our u vector before we put it on v. But we start the same way, where we draw a v that looks like the example they gave us. So it's a longish vector going off to the right, sort of shallowly. This is my estimate of v. And then for u, remember that we're flipping it. So instead of starting at the bottom right and ending at the top left, we're going to start at the top left. I'm going to say that negative u looks like that. So I'm going to start here, and again, just give an estimate. So, and I'm going to call this negative u here so that we remember that that's what that is. We flipped u. And then again, that sum, right, v plus negative u, is the line segment that starts at the beginning of v and goes to the ending of u. So this is v plus negative u. And so again, my pink line is my solution. Pink line is my solution. All right, so then we've got here that if v is equal to u, the v minus u equals 0, the 0 vector. The 0 vector has a magnitude of 0, so it has a length of 0 in any direction you please. So it can go in any direction, but it's got a length of 0, and that's when you have two vectors that are the same and you subtract them. The product of a scalar and a vector, so this is a different concept. It says the product of a scalar and a vector may result in the lengthening or shortening of a vector, a reversal of its direction, or both of these results. Vectors can also be written as ordered pairs starting at the initial point. And so this written as ordered pairs, that's the component form that we were messing with. And then this product of scalar is a number. Scalar is just a number. That's all a scalar is. It's a number. All right, so this is the continuation. It says the first term of the ordered pair is the horizontal distance, and the second term is the vertical distance. And again, that's that conversion from 2 points to component form, which is in those chevrons. So for example 4, we're going to write vector v as an ordered pair. And the way we are going to do that is we are going to identify its initial and terminal points, and then we're going to do that subtraction that we did with my example. So if I'm looking at v, I am going to call the point here in the bottom left 0, 0. We're just going to call that 0, 0. And that makes this point here on v the point 9, 3. And this point, the point 6, 8. If I want to write vector v as an ordered pair, which is in our component form, that is my terminal x value, my ending point, which is 6, minus my initial point, which is 9. And then I do the same thing with my y values, my terminal y value, which is 8, minus my initial y value, which is 3. Oop. It's supposed to be a chevron, guys. Like that. And when we simplify that, that is negative 3, 5. And so that is the vector v as an ordered pair. It's the vector v in component form. And what that tells us is from its starting point to its ending point, this vector goes to the left 3 and then goes up 5 units. So that's what that tells us. From initial point to ending point, this vector goes to the left 3 and up 5. All right, so if we want to do the same thing with vector w, I want to write it as an ordered pair. Again, I'm assuming that that bottom left point is 0, 0, which makes the initial point on w 5, 3. And my terminal point on w 3, 1. And so to calculate the ordered pair for w in component form, I take my terminal x value, which in this case is 3, and I subtract my initial x value, which is 5. And then I take my terminal y value, in this case it's 1, and subtract my initial y value, which is 3. And when we do that, we get negative 2, negative 2. So that's my vector w as an ordered pair. Now what this tells me is from its starting point to its ending point, vector w goes to the left 2 and down 2. So if I put down my starting point, I know I go left 2 and down 2, and that's how I get to my ending point. So that's a negative 2 and a negative 2. So my change in x is negative 2, and my change in y is negative 2. All right, so for number 5, they want us to perform the operations algebraically and geometrically. So I'll show you algebraically with the points, and then we'll talk about it geometrically as well. So if you have your vector in component form, addition, you just add x's and y values together. And the same thing with multiplication, you just multiply by the x and y values. You treat those chevrons as parentheses. So for vector v, our vector v is negative 3, 5. And we're going to add 2 times vector w, which is negative 2, negative 2. And we're getting the v and w from example 4, obviously. And so what you do first is you go ahead and multiply that 2 into the second vector, into vector w. And you just, like I said, you treat the chevrons as if they were parentheses. So what you get is, again, negative 3, 5, plus, and I've multiplied the negative 2 in, so now I've got a modified w. This is negative 4, negative 4. And then when we add them together, you add the x's and add the y's. So this is negative 3 plus negative 4, and then 5 plus negative 4. And what that gives us is negative 7, 1. And that's your component form. That tells us that we go from the beginning to the ending point. We go left 7 and up 1 from beginning point to ending point. That's what that tells us. Now, if we look at that graphically, if we look at it geometrically, because v comes first, v stays where it was on the other graph. So we go in at 0.93. So here's my vector. That's the initial point for v. That's my terminal point for vector v, and I'm going to draw it here. And again, that's exactly as it was in example 4 because it's my first vector. And then when we add, what we do is we draw the second vector that is stated in the problem with its initial point at the end of our first vector. And so for vector w, that means my initial point is there at the end of vector v. Now, because I have multiplied by 2, instead of going left 2 and down 2, like we would have done in example 4, and like W does in example 4, because of that multiplication, we go left 4 and down 4. And so from this point, if you count left, 1, 2, 3, 4, and count down 1, 2, 3, 4, that's your new W. This is my 2W, is what that is. And again, because I multiplied those distances by 2. And then remember that your sum of the two is the vector that goes from the initial point of your first one to the ending point of your second one. And so here it is right here. This is v plus 2w. And you'll see that v starts over here at 9, 3 and ends over here at 2, 4. And so, in fact, from starting to ending, from start to end, v plus 2w goes left 7 and up 1. And that's right there. Left 7 and up 1. So vector v plus 2 times vector w is -7, 1. And again, we can do that algebraically, but we can also do it with the graphs here. And there's one more thing I want to show you guys that's not on this notes page, and that's if you have a vector and you are asked to multiply it by a number or make it negative, that's a really easy process. So if I've got this vector u right here, and I'm asked to find 2u, you just make that vector twice as long. And so what we do is I can see about how far this vector comes, and I just extend it in the same direction about double its length. And so here is my 2u, like that. If I wanted to have negative u, what we do is we take that and we make both our x and our y's negative, and so that means that this vector ends up, and again we're just estimating, ends up down here in the third quadrant. This is -u right there, because I took both the x values and the y values and made them negative. And then last, if we're going to multiply u by 1/2, for example, what you would do is you just, again, our original u is the black vector right here under the pink one right there. And if I want to multiply that by 1/2, it just, again, starts in the same place but goes up half the distance. So that's 1/2 u right there. And so, multiplying vectors that start at the origin, you just, extend them out. Making them negative, you make both your x's and your y's negative. And then multiplying by 1/2, making them shorter. Again, they start in the same place, they just become half the length, or a third. If you multiplied by 1/3, it would be 1/3 the length of the original vector.